Okay, so we'll get started here. And is that the sad results of the Dodger game here? Yeah. Huh? Yeah, I know. Wah, wah. That's a postseason. Crush your hopes and dreams. Only one team can win. So, okay. Let's talk about confidence intervals. Okay, so this is now chapter 6. Okay, so in chapter 5 we were talking about sampling distributions, and we said, you know, if we have this population with this mean and this standard deviation, and I were to randomly take samples out of that population, what will our sample means look like? Okay, what is the distribution of y bar? That's what we were asking. So that's nice and all for kind of these theoretical thought experiments, but in real life, we don't know what the population looks like. We don't know its mean, we don't know its standard deviation, and generally the question we have is, can I look at this sample and then say something about the population? Okay, so over here we have the population, but the mean is unknown and the standard deviation is unknown. Okay. But maybe we can still manage to obtain a random sample. Okay. And here's our sample. And our sample of size n has, you know, mean y bar and has standard deviation s. Okay? And we want to say, well, I don't know the population. I don't know the mean of the population. I don't know the standard deviation of the population. But here I've got, you know, a random sample. And based on what I see in my random sample, can I make a conclusion about, in particular, can I make a conclusion about the mean of the population? Okay? This is what we are asking. Based on what I observe in my sample, can I make a conclusion about the mean mu of the population? Okay. This is what we want. Okay, so the example in the book is we've got, you know, these. This is my attempt at drawing a butterfly. Okay, and what we're looking at is we're looking at the wing area of butterflies here, okay? This is an important question. All right, so we want to know, so somehow we obtained a random sample of 14 butterflies. Or what could be assumed to be a random sample of 14 butterflies, and the mean wing area of these 14 butterflies is 32.81 square centimeters, and the standard deviation S is 2.48 square centimeters. Okay, and so here, here's our data, and we want to ask, what can we say about the mean of the population? All right. So what do you think? Do you think we can say anything about the mean of the population?
It's probably around 32, I think.
Okay, so we can say it's the mean of the population we expect to be somewhat close to 32.81, but how close? This is a good question. Okay, so so put this thought on hold, and I'm going to draw a picture, tell a little story. Not the greatest story ever told, but okay, so here we go. This is what is this? It's supposed to be a dog, okay? It's a dog on a football field at the 30-yard line, okay? And this is on Instagram now, and so it says hashtag invisible owner. Where is he? Okay, so this is not just a dog, it's a dog going for a walk with an invisible owner, okay? Okay, and we want to know, where is the invisible owner? Well, we have something to help us out. Invisible leash. Elastic. These are the worst hashtags ever. Okay, so we have we know that the dog is on an invisible leash, and we know the behavior of the dog and the invisible leash. Okay, so we know the behavior of the dog and the elastic invisible leash. Okay, and the behavior goes something like this. Okay, it's a stretchy leash, but the dog doesn't like to pull very hard against it. So 68% of the time the dog is less than 1 yard from the owner. Okay, but every now and then he finds something interesting and will pull against the leash. Okay, and such that 95% of the time the dog is within 2 yards of the owner. And then, what do you think this last thing will say?
3 yards.
Yeah. Okay. So, every now and then the dog will find something really interesting and pull a decent amount against the leash, and will be, but will still remain within 3 yards of the owner, and only in very rare circumstances will the dog pull very hard against the leash and be more than 3 yards from the owner. Okay, so based on what we see the dog at the 30-yard line. What can we say about the location of the owner? So we can't be entirely certain where the owner is, right? Could the owner be 3.5 yards away from the dog? It is possible. It would mean our picture was taken at one of those very rare circumstances where the dog was pulling very hard against the leash. But it is possible that the owner is, more than 3 yards away from the dog. But based on what we understand about the dog, we can say something like, I am 95% confident that the owner is located between what and what?
28 and 32.
Yeah, between 28 and 32 on the field. Does that seem reasonable to state? Okay. And if I want to be more confident, I can say I am 99.7% confident that the owner is located between 27 and 33. Or something like that. Or I can decrease my confidence to get, a smaller range. Okay? But, even if I'm 99.7% confident, can the owner be at 33.5? Yes. The owner could be at 33.5, but that means we happen to take this picture at one of those relatively rare occasions, or not relatively rare occasions where the dog was more than 3 yards from the owner. Okay? But because the owner and the leash are invisible, we have no idea whether that is the case or it isn't the case. We're just kind of assuming that, or we're hoping that we were not that unlucky, or lucky, however you look at it, that for the picture to be taken at one of those strange moments. Okay, so I'll write that here. The owner could be at 33.5, but that means this photo was taken at an unusual time, or unusual time when the dog was more than 3 yards away from the owner. Okay, so let's go back to our confidence interval then. Okay, so this is supposed to be an analogy where the location of the dog is what we observe, the y bar, our sample mean. So we know the value of our sample mean, we know the location of the dog. Okay. The location of the invisible owner, this is mu, okay? So the location of the invisible owner is unknown to us, and that would be the mean of the population. Okay. And we know the behavior of the dog in the invisible leash. That is the central limit theorem. The central limit theorem states that y bar comes from a normal distribution centered at mu, so that we know that y bar 68% of the time is within 1 standard deviation of mu. 95% of the time is within 2 standard deviations of mu, and 99.7% of the time it's within 3 standard deviations of mu. Okay? So we know the behavior of y bar because of the central limit theorem. So earlier today we talked about sampling distributions, the behavior of y bar in terms of where it ends up located in relation to mu. So when we are faced with a situation like this butterfly thing, we can see y bar, and we have a standard deviation of our sample, not the standard deviation of the population, but because we know y bar comes from a normal distribution, we know that the population mean mu cannot be super far away from y bar. Okay? And so just like here, I was making statements of confidence about the location of the owner, I can now make statements of confidence about the location of mu, the population mean. Okay, so let's formalize that. Okay, so I'm going to write, because we understand that y bar comes from a normal distribution centered at population mean mu. Okay. We can be confident that mu will be close to y bar. Okay? And so we can say something like, I am 95% confident that mu is between y bar minus essentially 2 standard deviations and y bar plus 2 standard deviations. Okay, and I put it in quotes because technically, if we look at the normal distribution for the middle 95%, it's technically actually 1.96, okay? And what is the standard deviation of our sampling distribution? Remember earlier today we talked about when you have a sampling distribution, if the population has standard deviation sigma, what's the standard deviation of our sampling distribution? Sigma over the square root of n, right? So we're talking about standard deviations of our sampling distribution. Is that okay? So I can say something like, I am 95% confident that mu, the population mean, is between y bar minus 1.96 and y bar plus 1.96 sigma over the square root of n. Is this okay? Getting to this point here. Are there any questions here? So there's a notation. We can just combine the plus and the minus together. And we might write the CI, 95% CI is y bar plus minus, we put it all together in one symbol, 1.96 sigma over the square root of n. Everyone's silent, so I don't know if this is a good sign or a bad sign. Are we okay with this? Yes, question. No. The 1.96 comes from when I look at the normal distribution. Okay, if I said I want to shade 95% in the middle, how much will I have shaded over here? And how much will I have shaded over here? Or on outside. I would have 2.5% on each tail, right? So if I look up 0.0250 in the table, this corresponds to negative 1.96, z equal to negative 1.96. And this one would be positive, z equal to positive 1.96. So it's, you know, we just kind of, with empirical rule, we say like within 1 standard deviation, within 2 standard deviations is 95%. But technically within 2 standard deviations, it's just ever so slightly more than 95%. And if you want about exactly 95%, you would use 1.96. Okay? All right, is this okay though? Does anyone see a problem with this though? Or an issue that we might encounter when trying to figure out our standard, our confidence interval? So keep in mind, what do we know about our population? We don't know anything about the population, right? When we look at the population, the mean is unknown, mu is unknown, and sigma is unknown, okay? And we're making our confidence interval so we can make a conclusion about mu, okay? But our confidence interval, what does it require? It requires that we know sigma, okay? So we're in trouble because we don't know the standard deviation of the population. So how am I going to, what should I do? What can I do? What information do I have available to me? The only information I have that tells me anything about the population is the sample that I have, right? So I've looked at my sample and I can find the sample mean. I can get y bar. So this gives me an idea of mu in the population. But if I want to make a statement about mu, I gotta know the standard deviation of the population. I don't have that.
You can find it though with the formula, right? Sigma over the square root of n?
I can't, well, I don't have sigma, but well, so we'll assume that we can't take more samples. Well, even if I took more samples, I still don't know the population standard deviation. I do have, though, I do have my sample standard deviation, okay? So I do have S, my sample standard deviation, yes?
Could you set that equal to 1.96 sigma over the square root of our sample size then?
So we're going to plug in the information we know. We know n, we know our sample size, okay? And that's it, okay? So we don't have sigma, we have S, okay? So I'm going to, the only thing I really can do to kind of get at this number is just guess what it is. But I'm going to take an educated guess, which is I'm going to take the standard deviation of my sample, okay? So I'm hoping my sample is representative of the population because it's a random sample. And I'm going to take the standard deviation of my sample. And I'm hoping the standard deviation of my sample is somewhat like the standard deviation in the population. Does that sound like a reasonable thing to say? It's reasonable in the same way that it's reasonable to say that your sample mean is probably somewhat like the population mean, okay? However, we're introducing another layer of uncertainty, right? We don't know if my sample mean, or sample standard deviation is too big, or if my sample standard deviation is too small. So we have to compensate for this additional uncertainty. And so to kind of give us some breathing room, what we're going to do is we're going to change the number from 1.96 to just something a little bit bigger, okay? So to kind of give ourselves some more breathing room, we're going to just make it bigger. So if we want to be confident about setting a zone where we think the owner is, let's say, you know, we're not sure about the properties of the leash anymore, we can just kind of make up for our uncertainty by just setting a bigger zone, right? So that's what we're going to do, okay? So let me write all of this, okay? There is a problem, okay? We do not know sigma, okay? So we will use our best guess for sigma, okay? Which is our sample standard deviation, S, okay? However, using S in place of sigma introduces additional uncertainty okay, so we must compensate by adjusting the value 1.96 to something larger. Let me fix my handwriting here. Conceptually, are we okay? Kind of? I hope. Okay, so we're going to talk about how we compensate this 1.96, okay? And so this introduces a new table called the T table, all right? And the T table is basically an adjusted normal distribution. It's just the normal distribution but kind of spread out. And it takes into something called degrees of freedom, which, I don't know, kind of, well, I'll get to that in a moment. But basically, if I have a big sample, if my sample is large, I can be more confident that this sample will give me a standard deviation that's pretty close to the population standard deviation. If I have a tiny sample, if I only have like 4 people in my sample, the standard deviation of these 4 people will probably not, well, has a big chance that it's not super close to the population standard deviation, okay? So I have more uncertainty if my sample size is small than I do if my sample size is large. And so the t-distribution takes that into account. When you have a big sample size, the adjustment factor from 1.96 is pretty small. If you have a small sample size, you adjust from 1.96 to something much greater, okay? And so if you have your t-distribution tables, so if you pull out your reference table, I think it's the second page, the amount we compensate is determined by the t-table, okay? With large samples, okay, we compensate very little. Okay, and with small samples, we will need to compensate more. So let me pull out this our t-table. Let you guys finish copying. Okay, so this is the critical values of the student's t-distribution. There's a fascinating story about the t-distribution. It was kind of discovered, or I don't know, what do you say about math? Is math discovered or invented? It was created. These values were created by a quality control guy at the Guinness Brewery in Ireland. He was in charge of tasting things or testing them for pH and making sure that they were within tolerance, and he would test them, and then he would say, this thing is no good, you know, send it back. And then they would do further testing, and they'd say, no, what are you talking about? It was fine. And he was like, well, what's going on? You know, my math says this should be bad, but it turns out to be okay. And it was because he was using what he thought would be correct, which was the normal distribution, but what he needed to do was be using the t-distribution. Now, of course, he didn't know that there was such a thing as a t-distribution, and so he did a lot of work, this manually intensive work, but he created the t-distribution as a result. But his name was not Student, and his name was Gossett, and the Guinness Brewery had this kind of thing that they didn't want these publications to be traced back to Guinness Brewery, so they forced all of their researchers to publish under pseudonyms. So he used the name A Student and became known as the Student's T-Distribution. Anyway, so it was beer. We have beer to thank for the T-distribution here. So you can see, if you look at your distribution table, at the very bottom, we have something called confidence levels. And so if we look at 95% confidence, we see the very first number at the bottom is 1.96, okay, which is the same number we would use for the normal distribution. And we see this corresponds to, in our column, what's known as degrees of freedom infinity. And so this means if your sample size was infinity large, you would have the normal distribution. You use 1.96, okay? Anything less than that, you have to make small adjustments. Degrees of freedom is factored in here. So, you know, when we take small samples, we compensate more. Our degrees of freedom, df, is equal to our sample size, n minus 1. So this is the formula that we use for determining our degrees of freedom. So if we have a sample of size 1001, we would have 1,000 degrees of freedom, and I would have to compensate for our unknown s just by a tiny bit by using 1.962 rather than 1.960. Okay, but for everything else, so let's say I had a sample size of 30, I would have 29 degrees of freedom, and instead of using 1.96, I would use 2.045. Or am I reading this correctly? 29 degrees of freedom? Let me see. Because n is 30, so we have 29 degrees of freedom. Yeah, 2.045. Okay. Is that okay? And so when you have even smaller samples, going all the way up to the top, if you have a sample of size 2, so that means you just have 2 people selected, right? Then your standard deviation is going to be will be very hard to use. So you have to compensate a lot by using this ridiculously large 12.7, which is huge. But you know, as soon as you get something like 10 people, you know, the amount you have to compensate is a good amount, but it's not terrible. 2.262, so that's about 12% or something. Yes, question.
So what would it be if it was 1001?
So your degrees of freedom is n minus 1.
Right.
So with a sample size of 1001, you would have 1,000 degrees of freedom, and your value you use is 1.962. Okay? And so just to be on the safe side, there's a recommendation that if you don't find your exact degrees of freedom in the table, always round down. So, you know, if you have a sample size of 40, you would have 39 degrees of freedom. And the recommendation is, rather than using the number associated with 40 degrees of freedom, round down just to be safe and use the number associated with 30 degrees of freedom. Of course, if you have a computer, you can find these values for any degree of freedom, because it's all built into its system there. Is that okay? So, and not everybody does this, but the recommendation, if you cannot find the exact DF, round down to the closest DF available. Okay. And that's just to be safe. It's better to give yourself extra cushion than not enough. So. Okay, so let's look at our monarch butterfly data and make a confidence interval. What were the values I had? Oh yeah, there they are. Okay. Okay, so let's make or the mean wing area butterflies. So we have a sample of 14. We have a y bar of 32.81 and a standard deviation of 2.48. All of these are centimeters squared. Okay, so let's do a 95% confidence interval, and that would be y bar plus or minus. Okay, and so I'm going to write t star to indicate this is a value coming from our t table, times, instead of sigma, we have s over the square root of n. Okay, so if we wanted to look at the components of a confidence interval, this part, the y bar, this is our estimate based on the sample. The t star is also known as our critical value. And this whole thing, s over the square root of n, this is called the standard error. So essentially, the standard deviation of our sampling distribution, or our estimate of the standard deviation of the sampling distribution. Maybe I'll write that out. So keep in mind that the sampling distribution has a standard deviation of sigma over the square root of n, and s over the square root of n serves as our estimate of that. Okay, so let's plug in the values that we can. And I think that's all of them. So it's going to be 32.81 is our y bar. And we're going to have plus or minus t star. So what is the t star that I'm going to look up? I'm going to have 13 degrees of freedom and confidence of 95%. So the value I use for 13 degrees of freedom, 95%, 2.160. Times s, 2.48. divided by the square root of n, square root of 14. Okay, so then now it's just a matter of punching this into our calculator. 2.160 times 2.48 divided by the square root of 14. I get 1.432. So I'm going to have 32.81 plus or minus 1 point, I'm just going to round off to 1.43. Okay, so if I do 32.81 plus 1.43, I get 34.24. So on our high end, on the low end, .38 centimeters squared. Okay. Is this okay? The math and all of this? All right, so here's the important part, the interpretation. What is this a confidence interval for? It's for the what?
Mean of the population.
Mean of the population. So that's the key thing, okay? It's not we're not going to make a statement about the location of the sample mean. Okay, we're making a statement about the unknown location of the population mean. So I would write, I am 95% confident that the mean, so what is our population that we're talking about? So we took a random sample of 14 monarch butterflies, apparently male monarch butterflies. Okay, so I would write, I'm 95% confident that the mean, and we're talking about wing area, so that the wing area of all male monarch butterflies, so, you know, I probably don't need to say this, but I will. So in the population, so, you know, we're 95% confident that the mean wing area of all butterflies in the population is between 31.38 centimeters squared and 34.24 centimeters squared. Okay. How does this feel? Okay? All right, so then I'm going to write a statement here, and you tell me if this is true or false. Okay, so this is true. Okay, this is the correct interpretation of our monarch butterfly confidence interval. Okay, we are 95% confident that the mean wing area of all male monarch butterflies is between 31.38 centimeters squared and 34.24 centimeters squared. All right, so I'm going to write this statement, and you tell me if you think this is true or not. Okay, so I'm going to say there is a 95% probability the mean wing area of, I'm just going to write, male monarch butterflies in the population is between 31.38 centimeters squared and 34.24 centimeters squared. True or false? Okay, or false or true? Do we have an opinion? So Justin says false. Anybody else feel one way or another? Okay. Do you have a reason why you're choosing?
It sounded right.
It sounded right?
No. Yeah, I don't see how saying you're 95% confident equates to a probability with the mean.
Okay. All right.
Maybe I'm totally wrong because it's like 9:30 at night.
Yeah. Okay. Okay. Well, this is not true. Okay. We cannot say this. All right. So we are 95% confident that the mean wing area of male monarch butterflies is between this and this. But does that mean there's a 95% probability that the mean wing area of male monarch butterflies? And the answer is No. What's going on is that the population, if the mean wing area of male monarch butterflies in the population is some number, okay? It's fixed. There's no uncertainty about that number, okay? So when we talk about probability, it only makes sense to talk about probability of uncertain events. Okay, so I like to do this dumb illustration here. So I've got a coin, okay, and I'm going to just ask you a question. I'm going to flip the coin, and what's the probability that this coin lands heads? And you say 0.5, and that's correct, right? The probability that this coin will land heads is 0.5. So I flip it, okay, all right. What is the probability that it landed heads? Okay, so you're a little confused because it feels like I'm asking the same question again, and you said 0.5. Okay, now watch what I do. Okay, what is the probability that it landed heads? Okay, and so I've deceived you, or I've tricked you, because it is not an appropriate question to ask what is the probability of an event that has already happened, okay? There's no more uncertainty about whether the coin has landed heads or not. You don't know whether it has landed heads or not, but there's no more uncertainty. It no longer makes sense to talk about the probability of the coin landing heads or tails, because it has happened, and when you say the probability of something, it only makes sense when we're talking about things with uncertainty. There's no more uncertainty, it's determined. So yeah, you can say 0 or 1, but it's actually not even true because it's not a probability. It either has landed heads or it hasn't, even if you don't know what it is. So at this point, all you can say is, I am 50% confident that it has landed heads. Okay? So in the same way, when we're talking about, it landed heads, by the way. When we're talking about the mean wing area of butterflies in the population, that is a number that's set, okay? If we could freeze time right now, we could find all the butterflies in the world. This would be the population of monarch butterflies. We could measure the wing area of all of them, and we would get the true mean wing area of all butterflies. There's no probability associated with it. However, that is unknown to us, and so we can only make statements of confidence. It is not correct for us to make statements of probability. Is that distinction clear? Okay, so this is, we cannot say this. Okay. The mu of the population is some fixed value that has no uncertainty associated with it. Okay, so it is improper to talk about probability. The only random or probabilistic element in this process is what? What is the only random or probabilistic element in this process of creating a confidence interval? The sampling. It's only that step. Only the random sampling has a random element of kind of this uncertainty. Okay? But once you have selected your sample, either the sample and you create your confidence interval, your confidence interval either has the mean value of the population in it or it does not, okay? Just like, you know, when we take a picture of the dog going for a walk with his invisible owner, okay? When you take that photo, either the owner is within 2 yards of the dog or he's not, okay? We don't know. We're just saying, based on our understanding, we're 95% confident that the owner's within 2 yards of the dog, okay? In the same way, we don't know whether our sample is a, quote, good sample or a bad sample. We're just saying, based on our understanding of the sampling distribution, we're 95% confident this sample is within 2 standard deviations of the population mean mu. Okay. So, you know, when we talk about 95% confidence, what does this mean? This means that if we repeatedly took random samples so if we repeatedly took random samples and created a 95% confidence interval for each of our random samples, then we would expect 95% of the confidence intervals we create to capture or contain the actual value of mu. So this concept of 95% confidence, or whatever level confidence we select, it comes from the idea of if somehow we were able to repeatedly take random samples, how many of our confidence intervals would get the true value of mu in it? We would expect, you know, in the long run, 95% of them to get the true value of mu, okay? Of course, if you did 100 random samples, you get something around 95, but not necessarily 95 exactly, okay? So in the long run, if you took thousands and thousands of random samples and you created a confidence interval for each of them, we're expecting about 95% of those to get the true value of the population mean. Okay. We are always making statements. We are making statements about the confidence interval for the mean of the population. Okay, so so in case this, so I'll just say this. Okay, so our confidence interval always makes a statement about the mean of the population. Okay? So we might say it's a, you know, a CI for mu based on y bar. We might also write something like that, okay? So our confidence interval says nothing about future samples. I'll say, you know, future samples or individual values. or, you know, the mean of our sample. Why would we not make a confidence interval for the mean of our sample? Because we know the mean of the sample, okay? It doesn't make sense to say, you know, I'm 95% confident that the mean of the sample is between here and here. No, we actually know that the mean of the sample is this value. I'm 100% confident that the mean of my sample is 32.81. I don't have to say anything about that, okay? And it says nothing about future values. So future values of that we might draw, like the next randomly selected monarch butterfly that I select, we can't make any statements about that, okay? This is just about the mean of the population, which is some unknown quantity to us that we are expecting to see, okay? So just a quick, so let's, just a quick check of our understanding. If I wanted to make a 100% confidence interval, could I do that?
Only if you could count every member of the population.
Okay, so, well, okay. Yeah, so one way would be to count everybody in the population. That's the one way to get 100% confidence, but then I would just have the mean of the population. If I didn't have the entire population sampled, the only way to have a 100% confidence interval would be I'm 100% confident it's between negative infinity and positive infinity, or maybe you could say 0 and positive infinity, but that's the only way to be 100% confident about anything, or, you know, if you're dealing with a percentage, you're 100% confidence between 0 and 100. So it doesn't make sense to talk about a 100% confident interval, okay? And also, you know, we wouldn't do things like a 99.999% confidence interval, because if we want to be really confident, what has to happen to our interval? It has to be really wide, right? So, you know, if I want it to be like a 99.999% confidence interval, I have to go, you know, plus or minus something like 10 standard deviations or 10 standard errors. And at that point, your interval becomes kind of useless, right? I can be, you know, I'm 99.99% confident that the average height of men is between 1 foot tall and 20 feet tall, okay? That's not a very useful interval to state, okay? You know, I can even be very confident that it's between 5 feet tall and 7 feet tall. Again, not incredibly useful. But, you know, if we want something that we can do something meaningful with, you probably need to get it down to within, you know, a few inches, okay? And then you would, so there's a balance between reducing your confidence level and whatnot, okay? So let's go back, or okay, so let's say, so we talked about the statement you can make. You know, I'm 95% confident, so let's say our confidence interval ends up being, okay, so let's do it for the heights of men. And we'll say 70 plus or minus 1.5 inches. Okay, so I'm going to say I'm 95% confident that the average height of all, you know, adult men in the U.S. is between 68.5 inches and 71.5 inches. Something like this. All right, so somebody asks, do we have evidence that the mean height is not 72 inches. No. Okay, so well, let's look at our interval. Our interval goes from 68.5 and to 71.5. So 72 is outside of our interval, right? So we would say yes, we have evidence that it's not 72. Can we be 100% sure? No, we can't be 100% sure about really anything in life, except for things that we already know. But we're going to just have to say this does provide evidence. Okay, so this is the best we can do. We're going to say we do have evidence. Okay, and I'm just going to write that mu, meaning the mean height of all men in the United States, is not 72. Okay, and that is because 72 is outside of our confidence interval. Is that okay? All right, and on the other hand, somebody could ask, do we have evidence that it's not 71 inches? And what is our answer here? So our answer here is no, okay? 71 inches is within our interval, within our confidence interval. So it is a plausible value for mu, okay? Or we would say we do not have evidence against 71 inches. Okay. All right, then somebody else asks, do we have evidence that the mean is 71 inches? And what would he say here? Okay, and the answer here is no, okay? And that is because even though 71 is inside our interval, we cannot, it doesn't prove that it is 71. It doesn't, our data can never actually be used to say something is a particular value. Okay, because the only way we can have evidence that the mean is 71 is if we look at the entire population, get the mean, and then if that mean is 71, that's the only way we can prove that the mean is 71. Okay? All we can say is 71 is plausible, or is plausible, but that does not mean we have evidence that it is 71. Okay? So our evidence can never be used, or our data can never be used to make a statement like we have evidence what mu is equal to 71 or some other value. Okay, our data can only be used against certain values. We can just say we have evidence that it's not 72. We have evidence that it's not 68. We have evidence that it's not these numbers. Okay? Numbers within our confidence interval, we just have to say, it's plausible. I can't reject that number, but we can't say, oh, for sure it's that number now. Okay? Even the number 70, which is right in the middle of our interval, our sample doesn't provide evidence that the mean is 70. It just says, well, that's what we got in our sample, so it's a plausible number. But as far as what is the actual value in the population, all we can do is make an interval of confidence. Are there any questions? Okay, then we'll end there, and we'll see you guys next week.